yes, it's partly will be kind of propaganda for this field, which the more I think about this, the more I think it is really kind of very exceptional in its diversity and richness of known and potential results, kind of comparable only with symplectic geometry, which gets started and it goes and goes and goes. Many domains just develop, they reach maturity and they stop. And this goes for quite a while. And so let me start motivating. It is, I apologize to those who know very well the subject matter. And I want to introduce it to most people who never heard of scaly curvature, but still know a little bit of basic geometric terminology. So first definition, and it's tricky. So I must say, again, I recall when I was learning and could never understand the definition. Okay, you just write a formula, so what? And so the formula is like that. It is Riemannian manifold, your object. So you have a Riemannian metric G. It is written. And out of this metric, you look at a point. You use geodesic coordinates or use frame of orthonormal vectors. And you just add sectional curvatures. And sectional curvature at this surface is just surface, every two-dimensional, every two-frame defined surface. The surface has usual curvature, Gaussian curvature, whichever you call it, and add all of them for all pairs of that. You don't prefer the order. It may seem kind of unclear why you do that, because when you do that for S2, for the sphere, instead of 1, you get 2. And this already may be confusing. And in general, for sphere, it is n by n minus 1, so it's useful to remember it's about square of dimension for unit sphere, because one of the points of this theory, it's very much dimension kind of plays a crucial role here. Yeah? And we don't quite understand this role, but it's everywhere. And this number 2 is fundamental. You may say, why 2? Why not 1? Because 1 is reserved for more fundamental object than tangent bundle of the sphere, because this is the curvature of a tangent bundle, and you know, it corresponds to early characteristic 2, or early class of the tangent bundle 2. But the bundle which has early number 1 is square root of this, and this square root underlies much in the scaly curvature, and this square root is the Hopf bundle, and it has curvature 1. And this is square of this, and so curvature 2, nothing to do. So these numbers are not kind of joke, yeah. And the formulas are no joke, because all progress which was made by just understanding, using very, very simple formulas, completely, in a way, obvious was being written. But one day we were written, and then you use kind of general theorem. The theorem may be difficult, but they kind of, you expect them to be true. They kind of obvious, unless, you know, you expect them. These formulas, absolutely, there's no way, the reason why to expect them. They are just there. And by the way, I observe that this sum doesn't depend on the frame, and this Pythagorean theorem. So Pythagorean theorem, of course, everywhere in differential geometry and everywhere in the world. But square root is a tricky matter. And so just to a little bit the exercise, if you have hypersurface in the Euclidean space, and then you don't, so of course curvature in the Riemannian manifold are tricky, but if you have just surface in dimension 3, you understand perfectly well. You can write down at every point, it's a function, and function has first and second derivative, a tangent plane, so it becomes on the second derivative, so they have matrix, and their principal curvatures. These are eigenvalues of this quadratic form. And then this very nice formula, it's square of the mean curvature minus square of the norm of the second fundamental form. So it's sum of all eigenvalues squared. And this dimension 2 in all dimensions, if you have in the high dimensional space. And if you look in the sphere, then you have a similar formula, but there is extra term coming from the curvature of the sphere. It's no scaly curvature of the sphere of dimension n, but scaly curvature of sphere of dimension n, small z. So, and these are fundamental formulas, and they, just using these formulas properly understood, you can derive kind of quite unexpected corollaries, which I shall explain, which by no means obvious before you have this kind of argument. Now, what are now the description? So these are formulas, and so, well, formulas are formulas. This, of course, nice formula, but how you can come to this formula? There is one natural definition, and this certain fundamental, which can play a certain fundamental role in everything concerning scalar curvature, that scalar curvature given a metric, you write certain formulas which depend on second derivative of the matrix. So a second order differential operator. Secondly, this operator equivariant under diffeomorphisms. If you change coordinate system, it doesn't depend on them. Certainly, scalar curvature depends only on the metric. It's tautology. However, if you think in terms of the action, it's highly non-trivial condition. And the key point, it's linear in the second derivatives. Because many other there are differential operators you can take, not sum of the curvature, square of the curvature of this, whatever you do, but there is only one except for the scaling up to the scale. And here you have to use this normalization. Scalar curvature of the sphere is n, right? And once you use the right normalization, you have these two fundamental properties, and they're clear from the original definition. And this is the fundamental property is that you multiply two manifold scalar curvatures add. And this, of course, immediately brings you to your mind entropy. So it behaves a little bit like entropy, yeah? And because it's come from physics, it may be serious relation to the entropy. And actually, in this normalization, interesting, if you normalize it to scalar curvature 1, you expand the sphere and make it scalar curvature 1, it has a radius square root of n, square root of radius n, yeah? And this is like unit energy per particle or something which you have in statistical mechanics. I may be wrong actually with these numbers. Right, it's radius n, yeah. And then that's square root of n. I'm always confused about that. And then if you look at this example, if you take multiply spheres, like S2 in power n, scalar curvature will be 2n, and if you get sphere of the same, it will be much bigger. And this also crucial. Yeah, it's sphere has the simplest kind of object has a kind of visible unit sphere, is scalar curvature about n squared. Now, it is common when people speak scalar curvature, they want to give geometric interpretation. And then they say, well, yes, you look at very small balls around one point, and this is encoded by the volume of the ball. And if you don't want to write a formula, which actually I don't remember, in any case, you can use this property. So if at one point you have two manifolds with the same dimension, in scalar curvature at some point at one is strictly greater than another, then volume of small ball will be like that, but you don't know what is this epsilon. And I'm using point. If you have this property, additivity, and this one, then this normalization, with this normalization, you know the hyperbolic plane has curvature -2. And this I'm using because what you do, because you multiply these two, so 0, it means it have roughly the same volume as Euclidean space, and just you have to make little computation and verify this fact. But just from this property and additivity follows the scalar curvature of H2 is -2. This hyperbolic plane is curvature -1, this sphere of curvature 1. So it's already, I'm using that how different, knowing something in one dimension and the additivity gives you about reflection, something completely kind of in different world. However, so what's wrong with this property? We don't know how to integrate it. It tells you nothing about volume of balls in general, except for infinitesimal ball. These are ball in specified size, but you know nothing about smaller ball. I'm sorry, about a real ball. And therefore, this was never used. And except there is some conjecture by Alan Guth, which kind of in the opposite direction, but well, it may be true, maybe not, I personally don't believe it. But I'm pessimist. Now comes the question, what's the meaning of this scalar curvature being positive? Why we say positive rather than negative? So one motivation came from physics, comes from physics, and for some reason, kind of positivity of energy somehow related to positivity of scalar curvature, which I don't understand, I don't claim to understand. As for mathematics, of course, we are motivated by logic of usual positive curvature, because the simplest manifestation of positive curvature is convexity. And convexity has this remarkable property. If somebody is locally convex, it's globally convex. And exactly this local property of convexity, saying that what happens kind of if you look at the metric, instead of saying ball small, you say it grows slower, one slower than another, if it happens locally and happens globally. And there is another interpretation of that, saying that in a way, both positive and negative curvature, their local property, even infinitesimal property, integrates to the global property. For negative curvature, it's not so nice. It's only integrates under some topological conditions. And if you slightly relax curvature, and it will be already said like Ricci curvature, Scaly curvature, there is a theorem by Lockamp saying, well, nothing. If you say a manifold has negative Scaly curvature, manifold has negative Ricci curvature, you know nothing at all. It's just zero information. You may be very excited. Any manifold that meets symmetric, but it means zero information. It's so-called H principle, which tells you your local condition is useless for global purposes. You can play with this for topology, whatever, but you never derive from this anything useful for the global geometry, global topology, or whatever. However, it may have some uses, intermediate one. It gives you some orientation, it directs you, kind of tell you direction where to go, where not to go, but by itself, it carries no internal kind of structure. So you have to understand what does mean curvature positive, or more generally greater than something. And there was some indication a long time ago. There was theorem by Leon Green saying that if you have a manifold of positive scalar curvature, it cannot have very large injectivity radius. Injectivity radius must be definitely bounded, and the sphere is extremal in this respect. So if you have scalar curvature, even in integral scalar curvature, the manifold, average scalar curvature, greater than that, or greater or equal than that for the sphere, its injectivity radius will be bounded by that of the sphere, or the same scalar curvature. This is simple integration argument. That's about it. And it never goes anyway. And of course, there's a property about injectivity radius very kind of big, but still, actually, it's not that trivial at all when you go to the next level of that. And then examples. And so there are basic example, a manifold like sphere in all compact symmetric spaces, in all compact homogeneous spaces. Well, symmetric spaces has positive scalar curvature, except for the torus, which is flat, and its all curvature is zero. And all homogeneous spaces, the natural metrics also have positive scalar curvature. So it's a huge number of examples, they're basic examples, out of which you can build further examples. And here is some basic thin example. And this makes you ponder if there is much meaning to positivity of curvature. But you take a graph in this space, in the Euclidean space. This picture, of course, in the Euclidean space of dimension 3. If you take a thin neighborhood, and you see, because there's very short circles, they carry lots of positive curvature. And because of that, if you do it carefully at triple points when there is singularity, mean curvature will be positive. Sum of all principle, because you can compensate this kind of negativity kind of here by turning this by very short circle, if you do it carefully. And therefore, this neighborhood, boundary of this neighborhood is positive mean curvature. Now, mean curvature tells you also something about, of course, areas of surfaces. But if you do this graph, take this graph in dimension 4, then this, instead of one sphere, we have two spheres. And two spheres, this curvature scales this curvature is supposed to. When smaller the sphere, the bigger the curvature. So when you shrink the spheres, at every way curvature blows up, goes to infinity, and this little thing can be compensated. However, you must be careful. This can look very naive and simple picture. It has the following counterpart. That it's in dimension 3, you take this rotational thing, and also you can smooth it. It will have positive mean curvature. And of course, there are these dangerous corners you can do it. And if you rotate it in dimension 4, this thing will have positive scalar curvature. So it has very kind of ragged geometry. And so what you can say about it? Huh? So it looks very kind of, you don't expect much you can derive from that, neither geometrically nor topologically. What you can do with this, you can become later to that, you can develop surgery. This, of course, is the simplest kind of surgery. If you do it for graphs in four manifold. In the four space, you get some connected sum of product of spheres with this metric. So you have connected sum of product of spheres, so you have positive Scaly metric, but metric are very kind of not terribly interesting because all the structure hidden in this graph. But in a way, how is hidden? Not so simple. It's kind of a high dimension, of course, you have much more possibilities. And then come the first theorem. It was not first historical, but the first by its simplicity. And the proof, indeed, here is a full proof of the theorem. It says that if we have a three-dimensional manifold and take integer homology class in there, which is it's realizable by a surface, which must be sphere. And therefore, for example, for torus, where non-homology class is spherical, just tori, it cannot have metric or positive Scaly curvature. And the proof is just two lines, modular the following theorem, and the theorem is non-trivial, but kind of very naively obvious, that every homology class can be realized by a smooth surface, which minimizes area. And this kind of a difficult part of the proof. On the other hand, it's trivial part of the proof, because, well, this you can assume it. If physicists, by the way, had very similar results, and they assumed all this kind of course, regularity in existence, actually in a more complicated situation in Lorentzian geometry. Once you accept it, and then you just write this formula. This is a point-wise formula. If you have some manifold in any dimension, codimension 1, in manifold with any dimension, then there is this formula. This, you already met this, mean curvature squared minus second order, and then there is a term with Ricci curvature. What you have to know about Ricci curvature, it enters in another formula, even older, due to Bosff, of course. This formula was known, I don't know to whom, maybe to Gauss in a way, or to Riemann, and this is formula due to special case of the formula of Hermann Weyl, it's tube formula. Namely, when you move a surface, which is with zero mean curvature, if there is mean curvature, you must be careful, it's slightly ambiguous. If you have a surface with zero mean curvature, which is locally minimal, you move it in normal direction, in direction of this kind of normal vector. And look, so because mean curvature is zero, first derivative of variation of area of this volume is zero. But the second derivative non-zero, and this is the formula. And this is a, so you see, this formula says that y is Scaly curvature much smaller than x. Because if it's minimal, this term disappears. There is some Ricci curvature, but this may be uncontrollably large. So it has huge minus. So it looks hopeless. You can use it by induction. If you take minimal surface, for example, in Euclidean space, all minimal surfaces has actually negative Ricci curvature. It's like a negative Scaly curvature. However, if absolutely minimizing, it's quite a different story, because absolutely minimizing means when you move it, its area goes up. So its second derivative must be accordingly confused about the sign. That must be negative, that must be positive. But here's what you have. Scaly curvature is bigger than that. So when your second derivative is positive, when you move it, area decreases, increases. And so you have this inequality. Integral of Scaly curvature is positive. Though Scaly curvature looks much smaller than that of this manifold, it's actually integral becomes bigger. Right? Because this term now appears with different sign. And yeah, I hope I didn't put my sign correct. I always actually I just anytime I look at this, always time I come with wrong signs. Yeah, but this is definitely true. Yeah. From going from here to here, I have my signs. I hope you're correct. Yeah. Yeah. Okay, so therefore, if you take this minimal surface, this integral must be positive. In Gauss-Bonnet, dimension 2 says if you have the integral of the Gaussian curvature, Gauss curvature positive, then it must be sphere. It's oriented hypersurface, so it's oriented closed surface. Its integral of curvature is positive, therefore it's sphere. So, and this is, I'm pretty certain, Rick, but I would never publish this paper in so short. Yeah, I mean, it's kind of trivial. And their proof, their paper dedicated to showing, they give independent proof of classical kind of theory by that time, the existence of this incompressible minimal surface. I don't know, actually, it could have been actually the purpose of this paper, I don't know, but all this kind of completely I need it, and this is a proof. And this is the shortest paper by this guy. I think it's the best one, by the way. It was really absolutely unexpected. I mean, nobody would believe that kind of you can prove like that. That's your theorem. And this was a problem. Actually, this was a problem by Gerach in a slightly different form. And so Gerach was asking if on the Euclidean space you can deform a metric, flat metric, deforming only in the compact region and making Scaly curvature positive. Now, if you take Euclidean space and you can imagine it's a part of a huge torus, and you do it for the torus, and you have on a torus such a picture, and observe if somewhere zero, it's not strictly positive, but this kind of the proof. If you look at a second, the same argument applies. So, and of course, apparently this Yao and Schoen are motivated by physicists which is related to what they call positive mass theorem, which, well, of course, we will not discuss here. So, but this all I'm saying is kind of a prehistory. Yeah? All in my lecture with the prehistory of the modern kind of wave of development, where this was motivations. So I want to say this is the formula. This is a kind of, even Scaly curvature doesn't enter here. This is Gauss' formula written in convenient form. This convenient form, just the major organization is here. This what kind of this writing Scaly curvature in this form. Mean curvature squared minus second fundamental form. And what's the use of this fundamental? Only it's positive. So Scaly curvature equal to mean curvature minus summation. And this minus summation, despite this minus, it's in your favor. Well, of course, but this, of course, because this term comes also in the formula in Hermann-Weyl formula. So the more surface curved, the faster it shrinks in the normal deformation. This is a kind of simple thing, but this is kind of algebra in this formula. Okay. So we cannot have this y expected to have also positive Scaly curvature only with integral, but you know slightly better than integral. If you look slightly more carefully, and I explain it, what you know that there is on this product, there is T1 invariant metric, which has positive Scaly curvature. Actually, with constant Scaly, or you can make it with constant curvature, but you can't have it bigger. Of course, this is defined only on the submanifold, but where the two meet, one bigger than another, because invariant and the action, it only function y. Y is a part of x, so this makes sense, basically. And so I can say how you do that. You can do it by kind of analysis, linearizing, whatever, but you can see geometrically as follows. You have your hypersurface, and because it's minimizing, strictly minimizing, so when you move it, it becomes bigger, area bigger. So of course, it may be not strictly bigger, but imagine a strict minimum. So no matter how you move it, its area goes a little bit up. It means if you slightly perturb this equation, still there is minimal solution. So what you say, now it will be not minimizing, but you allow a little bit volume inside. Yeah, you imagine a little kind of balloon with two sides. Two-sided, you put a little bit air. So you put a little bit pressure. And then you get a surface, it will be surrounded by a little band, and this little band will have positive mean curvature. The fact it actually will be constant, it's constant in material, it will be positive. So you can include it in a very thin band, both sides of which we have positive mean curvature, kind of, a little bit, kind of almost convex. One, you have such, imagine you have such a narrow band in paper, just band to paper, and you start reflecting it with respect to each of those ends, and then become infinite cylinder. And so instead of this one band, you have infinite cylinder. Topologically, it will be y times the line. And then you make this widths of the band go to 0 and see what happens to the band. And then you can show it converges in the limit to this kind of metric. Now it will be not torus, of course, but real line. So torus is just, for some reason, good to say torus, but in fact, the truth, you have the covering, so it's a product, so it will be actually a real line. And you need to prove it, but it, you know it is so. And once you have it, you observe it has nothing to do with dimension 3. You can do it in any dimension. And if you had symmetry to start with, symmetry preserved. So in any dimension, and so far you have minimal variety. You just take minimal subvariety. If it was symmetric, it would be symmetric. You arrive at an even more symmetric thing, and you symmetrize it to the end. So only this kind of symmetrization in different terms was come from the paper of Rick with I forgot his name, Calibri, whatever. Somehow I have a problem with names. Now with my age, I can have this problem. And Calibri, Fisher Calibri. And so this shows that if you have a torus of any dimension, you argue a little bit, insofar as you have smooth submanifolds, insofar as you can realize hypersurfaces by smooth minimal varieties, they cannot have medical positive curvature. Okay, but then a little bit, that problem with singularities, nobody really was serious. There were recently various papers handling that, but it's still a little bit unclear what happened there. But conceptually, picture is quite clear, except, well, so geometry is still not understood, just topology. Now we look at what happened, what was happening before that. And actually, the first result of what came from completely different source, this theorem of Lichnerovich, and this was related to Dirac operator. This, again, is one formula, but now it's much trickier because the formula depends on spinors and Clifford algebras and this kind of mathematics. So this is a mathematics which goes into their algebra. It's again linear algebra in a way. Once it's written down, it's kind of obvious. You have to write it down. And the special basic example of that, it's of course square root of -1 and complex numbers. And the thing is, IHES said this was a major contribution of mathematicians to humanity's invention of complex numbers. Because, you know, Feynman, somebody said, what is ascribed to him, that if there were no mathematicians around, development of physics would be delayed by 1 week. But I don't think there was a reason to physics would discover complex numbers. They covered completely by mathematicians, and when they came to physics, and it's Schrödinger who introduced them, and he was very unhappy about that. And apparently the idea he borrowed from speaking to Hermann Weyl. And complex number is anti-physical, and still physicists feel very unhappy to have this, function, complex varied function. The mathematicians really don't care why this should be real. Yeah, I mean, what should be real? Of course, complex was much more elegant than our reality. Real numbers are just artifact. And Clifford algebra generalized that. However, Dirac operator was invented by Dirac, but it was a long time after Clifford, of course, the complex numbers. So there is some remarkable operator, and this was discovered by Dirac, which is work on Euclidean spaces, functions, complex varied function on Euclidean space of this dimension, which I indicated, so big dimension, power of 2. And the square of this is Dirac operator, Laplace operator repeated as many times as you have. My number is here wrong. It must be, it's correct. Yeah? It's correct. It's on the Euclidean space, but n big copies of this. And of course, there is this example, this Cauchy-Riemann system. We can say, take a Cauchy-Riemann system, added together, we have this operator. But our operator is better. It's irreducible. It's not divided into sub-operators. And it has kind of maximal symmetry. So what is symmetry? And symmetry comes from spinors. And spinors correspond to taking square root of Euclidean rotations in the same way as complex numbers. So what you can explain to each other, what is number square root of -1? What is -1? Take a real line, turn it 180 degrees. But imagine this turn making the plane. Now turn it on 90 degrees. And it looks okay, so you have square root of -1. But miraculously, you can add them and you have a field So nothing cancels except for zero. There's no singularity in that. And this is absolutely unexpected. I mean, why? It happens only in one dimension. You can do it only in dimension 2. And this is so special about dimension. It can a little bit in dimension 4 like quaternions, and of course, special case of Clifford algebras. And then in general, it doesn't work that smoothly, but still it works remarkably well. You can kind of, it takes square root of Laplace operator, or it's kind of square root of rotations, because orthogonal group is fundamental group from dimension 3 on. It is of 2 elements, it takes covering this, and this will be a spin group. And nature loves this group. And nature loves this group because, well, it doesn't want to bother with fundamental group. It's too complicated from the point of view of nature. Why the hell you have to go twice and take this covering? You have the algebra, and so it's much simpler. So nature take only the simplest constant. In physics, spin is, everything is spin, yeah. Everything controlled by S to F, but not by orthogonal group, by spin. And so the symmetry is very simple. So you have but what is non-simple, of course, that in this dimension there is a representation of this group, and this representation is faithful, and there is no representation of smaller dimensions. And this is completely kind of remarkable. But for that reason, you can't understand spinors. There is no simple model for spinors except for dimension 2. You have the quaternions, more or less. You can absorb it, but then in high dimension, they have absolutely nothing with what you used to have. They have no, and they depend on the orthogonal group. They're not linear, like the algebra in a way similar to the, of course, exterior algebra Clifford. But there is no geometric interpretation, and you're not supposed to be, you're supposed to be unhappy with that, but you can live with that. And Atya was saying, systematically, you're not supposed to understand spinors. Nobody understands spinors. You cannot understand them. They don't fit kind of in our geometric experience, but you can use them. Algebra tells you what to do and what not to do. And there is this operator, and it has this symmetry. And because of the symmetry, on certain manifolds, it can define corresponding operators. So what you do, you have Riemannian manifold, take geodesic coordinates, pretend it's Euclidean space. At this point, take Dirac operator and extend to the whole manifold, except you may have run into trouble. So extending it, you may have abstraction. And manifold must be spin. Some topological condition imposed on manifold, those who knows, who don't know, we don't know. But this is, it excludes some manifolds. Some spin, some not. And then there is this formula. And this formula, this particular formula, the square of the Dirac operator equals something positive operator, positive explained in what sense, and plus multiplication by Scaly curvature is coefficient 1,4. Again, this 4 is fundamental. It's not a joke. Yeah. The world depends on this 4. And now, of course, when you define Scaly curvature, also there were some numbers involved. And then you say, this formula, it was due to Schrödinger, discovered by Schrödinger, and then was known apparently for Lichnerovich for some time. And of course, the remarkable thing is this operator, which was introduced in the common use by A.T. Singer, which of course was not present in this form in the work by Dirac, but Schrödinger exactly used it in curved space. So he knew this formula and was very kind of happy with this formula. And then you can say, granted this formula, you know, you cannot have harmonic spinors. Harmonic spinors solution of the equation, which is when I say harmonic spinors, I mean non-zero spinors. So there is no harmonic spinors. On the other hand, there is index theorem was proven in 1966 that if certain invariant non-zero, which I don't want to say what it is, there must be harmonic spinors, whatever is the metric on X. And this is very robust. Right? It's not just existence, but exactly saying how many of them, at least so many, in some sense. Yeah. A very robust theorem, and therefore, you cannot have here harmonic spinors because, again, by simple topology, you can check this invariant here is non-zero, whichever it is. And this was Lichnerovich done. And again, all this was known. And the point was just to invoke this formula. And an even easier formula, but of course, what's hidden behind it. And by the way, I don't know the simple proof of this formula. It all involved computation, and I'm pretty certain it must follow by symmetry. We know much about what kind of formula should be coming from symmetry alone, but I'm not certain you can really how to prove this without computation. You use some manipulation with Clifford algebras. Very simple, but you have to compute. So where you are at this point? Well, so there are this manifolds which don't admit positive scalar curvature, and then there's an example which exists, and there is a theorem saying that lots of a certain dimension, all manifolds admit such metrics, and for other dimensions there are counterexamples. And so for simply connected manifold, you kind of know the answer. And you see, some time ago, when I was learning topology, everybody assumed that if you handle simply connected manifold, then you know everything, and then there was a wall which kind of extended classical topology to non-simply connected ones, except there were no kind of examples of non-simply connected manifolds. At that time, people didn't know that really. So what are non-simply connected manifolds? Kind of a very funny ideas what fundamental group can be, but what a group can be, right? From modern perspective, simply connected manifolds are a negligible part of the whole world, yeah. Having huge invariant group and just being at 0 or 1 is just tremendously powerful condition. It throws away everything of interest. But, well, this was attitude. And you can say, well, thing was kind of handled, except there was kind of funny things. The torus was not covered by this theorem of Technirovich in slightly more general form by Hitchin, because for the torus, all this invariance is 0. So there is no reason why it should not have this metric, except that there was later this argument found by Shantiao motivated by physicists. And so we don't understand then. And then another question, what is about Euclidean space? It's simply as kind of space, topologically, what is all that tells you? It tells you nothing about Euclidean space also. So where we can go from here. And now the real story starts, right? So, and this, of course, it's 45 minutes, right, my lecture. So I'm coming to the end, and I try to just explain what we don't know and what we, where the whole thing went to. The next stage of that was a realization that there is a similarity between scaly curvature problem, topological scaly curvature problem. So far, this is topology. Geometry doesn't enter this. Between the topological scaly curvature problem existence, trying to understand which manifold support and which not metric with positive scaly curvature, it parallels to the problem from topology, which is Novikov conjecture. And the Novikov conjecture was asking, in its simplest form, says that if we have a spherical manifold, or K-pi1 manifolds, so the manifolds where there is no topology, it's universal covering is contractible, then it's characteristic rational Pantryagin classes, rational meaning up to torsional classes, are homotopy invariant. In simply connected topology, you can always change. Given homotopy type of manifolds, you always can find smooth structure which has any kind of Pantryagin classes you want, except for one constraint, the signature, which is some combination of Pantryagin numbers, and this is the only abstraction. But if manifold is non-simply connected, and moreover, if its topology dominated by the fundamental group, and all other homotopy group vanish, then opposite situation is rational Pantryagin. So up to torsion rational Pantryagin classes determined by fundamental group. This was conjecture. And Novikov proved it in a way for fundamental group for the torus, right? So for if you cannot change, you cannot produce smooth structure on the torus with non-trivial rational Pantryagin numbers, even cutting mode 2, yeah. And then, and this was done by surgery, a very kind of strange argument due to Novikov when he proved this topological invariance of Pantryagin classes. And then there was another proof also for the torus and for some other cases due to Lustig, who used their index theorem. And he observed that using index theorem, you can give very short proof of some result by Novikov. And it was kind of, you use just not Dirac operator, but the signature operator with coefficient in flat bundles, in flat, not orthogonal, but in flat bundles, and just you write some formulas for the signatures and just interpret them in proper way. And then there came work by Mishinka, who extended this to manifold with negative curvature. This was kind of strange and very bizarre development that he's shown. In particular, if you have manifold of constant manifold, compact manifold of negative curvature, you cannot change this topology with given homotopy type, produce topology of smooth structure, which is the same, that would have non-trivial Pantryagin classes. And the proof was kind of using infinite dimensional version of the index theorem. And then the same phenomenon happens with Scaly curvature. This kind of argument have their counterparts in manifolds with positive Scaly curvature. The same thing amazingly apply. And moreover, because here there is curvature, you have geometry involved. So the curvature takes certain value. It's not just positive. It has a number. And this number, of course, is not respectful of topology because you can scale it, but certainly tell you something about geometry. And from this moment on, we started to understand a little bit geometry of this manifold. However, the properties in a way are very weak, but in a way quite strong, and has kind of somewhat unexpected application. So I gave, from what I said, let me give some example of that. Let's return to this formula. At the very beginning, the formula which I want to write is, look at this one. So forget about this term and observe the Scaly curvature of submanifold equals something approximately n squared minus square norm of the second fundamental form. Now, in codimension 2, what can be this? Imagine I have curvature approximately 1, manifold curved by 1. Then this number will be about 1, so this term will be about n. But this term about n squared. So you see that even if you have curvature of in manifold which being in a sphere with curvature about square root of n, which is pretty curved, or slightly less than that, it's still, this term will be smaller if codimension is about square root of n. So we have some manifold of low codimension and moderate curvature, it also have induced positive Scaly curvature. In particular, torus cannot be there. So you cannot immerse torus in the sphere of, say, n-dimensional torus to the sphere of dimension n plus roughly square root of n with moderately large curvature. Torus. But exactly because torus admit the medical positive Scaly curvature applies to any other manifold for which you know, or like this Kummer surface or product of Kummer surfaces. But take any other manifold product of spheres, and you have no idea if you can do it or not. So here we don't add nothing, we mention Scaly curvature. We just take two examples of manifold. Say torus or product of Kummer spheres. When you put it to the sphere, which you actually can immerse, might be terribly curved, but about any other manifold, we have no idea. And this is kind of very bizarre situation, which with this, I would say our seminar not about only Scaly curvature. Scaly curvature points out the big gaps of our understanding of fundamental geometry. I think it is really the most fundamental aspect known about Riemannian geometry, and which tells you we have no understanding at all of basic texture, of the geometric texture, especially related to Scaly curvature. We don't know what is Scaly curvature in a way. We don't know what are the right objects, and this requires some discussion. So what we expect of the being objects. And so this is our, hopefully, in the course of the seminar, there were kind of huge amount of results in the recent years, more and more information being collected. It's become more, I think, than any other domain in geometry of this kind. And well, and we run every second in a very simple, natural question which we cannot answer. So here is question, I take product of sphere S2 by itself. So S2. For all we know, it can be immersed into sphere with codimension 1, curvature less than 100. Absolutely, we have no idea. Torus, somewhere stops, it doesn't work. But for the product of spheres, we have no ideas. And indeed, if you slightly modify it, there are some kind of tricky immersion saying that you must be careful what you say. So that is the end of my talk, I guess. Yeah, right. This is 45 minutes, right? I'm happy to answer questions. But again, I want to repeat that the field developing was remarkably better and better, very, very rich, but this only the beginning. So there is a feeling that it will go for many years to come, growing and for more than anything else, like symplectic geometry, which goes without stopping because there's so much structure there to discover. So it's the most structural aspect of Riemannian geometry for all we know, and again, it's technically the most sophisticated, the most interesting in this respect. So I'm ready to answer questions. I can probably return to the stop sharing. And so I expect somebody to ask me something.
Thank you very much. Maybe